In the spring of 2020, more than 14 billion miles from the control room monitoring it, Voyager 1 sailed into something nobody had predicted, and it has not stopped changing in the 6 years since. Over the course of about 8 days, the magnetic field surrounding the spacecraft suddenly jumped in strength by more than a third. Then it kept climbing for another year, eventually reaching nearly double its original value, before slowly declining back down again. Scientists gave this bizarre event a deceptively simple name, the magnetic hump. And in May of 2026, a team of researchers led by Ji-Woo Park, using data Voyager 1, has continued sending home in the years since that hump first appeared, published something that goes further than describing a strange bump in a graph. They found that the magnetic field's direction itself has been slowly, steadily turning ever since, and that the character of the space Voyager 1 is currently flying through looks measurably different than it did before the hump ever occurred. This is not a claim that physics has been rewritten. It's something more interesting than that. Real, direct, in-place evidence from the only instrument ever positioned to gather it, actively testing and refining our understanding of plasma physics in an environment no human instrument has ever had the chance to study this closely before. This is the real story of what Voyager 1 has actually measured, and why NASA and independent researchers alike consider it one of the most valuable ongoing physics experiments currently running anywhere in the solar system. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why a strange bump in magnetic field strength deserves this much attention, you first have to understand exactly what Voyager 1 is doing out there and why it remains, to this day, utterly irreplaceable. It launched on September 5th, 1977, on a mission designed to last about 5 years, a tour past Jupiter and Saturn before falling silent. Instead, it kept flying, and on August 25th, 2012, it crossed the heliopause, the boundary where the sun's constant outward stream of charged particles, the solar wind, finally loses its battle against the pressure of true interstellar space pressing in from the other side, becoming the first human-made object in history to leave the solar system entirely. It remains, along with its twin Voyager 2, the only spacecraft ever to have measured the space between the stars directly, rather than inferring conditions there from telescopes and models built from safely inside our own solar system's protective bubble. Everything Voyager 1 has told us about interstellar space since 2012 has come from a small number of instruments still functioning after nearly 5 decades. And one of the most important of those instruments is its magnetometer, a device specifically built to measure the strength and direction of the magnetic field surrounding the spacecraft at any given moment. Before Voyager 1 ever crossed into interstellar space, scientists had built careful theoretical models predicting what its magnetometer should find on the other side. The expectation was reasonably straightforward. The sun's own magnetic field, carried outward by the solar wind, should point in one specific, well-understood direction inside the heliosphere, and the moment Voyager 1 crossed into true interstellar space, that direction should shift to reflect the entirely separate magnetic field of the wider galaxy. It didn't happen that cleanly. When Voyager 1 actually made the crossing, its magnetometer found that the magnetic field direction barely changed at all across the boundary, a genuinely puzzling result that led some researchers to initially question whether the spacecraft had actually left the solar system in the way scientists believed. Nathan Schwadron, an astrophysicist at the University of New Hampshire who has spent years studying this exact problem, described the skepticism directly. There were, in his words, still naysayers regarding whether Voyager 1 had actually crossed the heliopause at all, precisely because the expected shift in magnetic field direction never showed up the way theory predicted it should. Schwadron and his colleagues eventually resolved that specific puzzle, though not in the way the original models anticipated. Working with data from NASA's Interstellar Boundary Explorer, or IBEX, a mission that studies the heliosphere's structure from Earth orbit by detecting energetic neutral atoms streaming in from the boundary region, the team found that Voyager 1's magnetic field readings were deviating by more than 40 degrees from what a truly pristine, undisturbed interstellar magnetic field should look like. Rather than concluding this meant Voyager 1 hadn't really crossed the heliopause, the team proposed something more nuanced, that the spacecraft had genuinely left the solar system, but was still traveling through a specific, disturbed region where the interstellar magnetic field gets deflected around the heliosphere itself, the same way a stretched rubber band gets pulled and bent as it wraps around a beach ball. Schwadron used exactly that image to describe the physics involved, explaining that the magnetic field lines out there are being deflected around the heliopause, rather than existing in some perfectly clean, undisturbed state the moment a spacecraft crosses the formal boundary. The research confirmed that Voyager 1 had genuinely crossed into interstellar space, while also explaining why the magnetic field data looked stranger than anyone had originally predicted, evidence that the transition zone immediately outside our solar system is more complicated and more gradual than a simple line on a diagram would suggest. That was the state of scientific understanding for several years. Then, in 2020, the magnetic hump appeared, and it gave researchers an entirely new body of data to work with. According to the detailed technical analysis published by Leonard Berlanga and colleagues tracking Voyager 1's readings from 2012 through 2023, the magnetic field strength jumped by a factor of roughly 1, 35 over the course of about 8 days in mid-2020, and proton density in the surrounding plasma jumped by a similar factor at the same time. Following that initial spike, the field strength kept climbing, reaching a peak of approximately 0. 56 nanotesla in 2021, before gradually declining back toward its pre-hump baseline value by late 2021, nearly a year and a half after the disturbance first began. That kind of sustained multi-year event, playing out across an environment as sparse and quiet as interstellar space is assumed to be, was itself a genuinely significant thing to have captured directly, giving researchers a rare extended natural experiment to study rather than a single instantaneous measurement. The May 2026 study, led by Jiwoo Park and including Berlanga among its co-authors, went back through Voyager 1's magnetic field data covering the full period from that 2020 hump event through the middle of 2025, specifically to understand what happened to the surrounding interstellar environment after the hump itself had faded. What they found was genuinely striking, and it's worth being precise about exactly what the research demonstrates. The magnetic field's direction has continued shifting, slowly and steadily, in the years since the hump occurred. And comparing conditions before and after that event revealed a real, measurable structural difference in the character of the surrounding interstellar medium. The research team documented what they describe as a temporal decoupling among different components of the magnetic field data, meaning different measured properties of the field began changing at noticeably different times relative to the hump itself, some shifting right around the peak of the disturbance, others continuing to evolve for years afterward. The team was careful to note, in their own published language, that identifying the precise physical trigger and exact onset of these directional shifts requires nuanced consideration, and that a full, detailed investigation into the chronological origins of these individual changes lies beyond the scope of that specific study, deferred instead to future research. That kind of careful, deliberately incomplete conclusion is worth sitting with for a moment, because it's exactly the sort of honest, measured language that distinguishes real, credible science from an exaggerated headline. The research team isn't claiming to have solved every mystery buried in this data. They're documenting with real precision that something genuine and physically significant happened to the structure of interstellar space in the region Voyager 1 has been traveling through, that its effects are still detectable years later, and that fully explaining why it unfolded exactly the way it did remains an open, ongoing area of investigation. This connects to a broader, actively evolving body of research, using Voyager 1's data specifically to test and refine plasma physics under conditions that simply cannot be replicated anywhere else. A separate study, published in July 2026 in the same journal, used Voyager 1 and Voyager 2's combined magnetic field measurements alongside IBEX's own observations to further refine scientists' understanding of the so-called IBEX ribbon, a mysterious circular arc of energetic neutral atoms in the sky that appears to trace the true direction of the pristine interstellar magnetic field, unaffected by the heliosphere's deflecting influence. Triangulating between multiple independent datasets, including the 2 Voyager spacecraft's own in situ measurements taken from actually inside the environment being studied, gives researchers a genuinely rare opportunity to cross-check theoretical models against real physical data gathered from 2 different, independent vantage points simultaneously, rather than relying on a single measurement or purely theoretical calculation. It's worth explaining plainly why this specific kind of research genuinely matters to the broader field of physics, without overstating what it actually proves. Plasma, the ionized gas that makes up the overwhelming majority of visible matter in the universe, behaves according to physical laws that are reasonably well understood in laboratory conditions and in the relatively dense environments found inside our own solar system. But the interstellar medium is an entirely different physical regime, extraordinarily sparse, extraordinarily cold, and, until Voyager 1 and Voyager 2 crossed into it, entirely unmeasured by any direct instrument. Testing whether existing plasma physics models hold up accurately under these specific extreme conditions, conditions that simply cannot be recreated in any laboratory on Earth, requires exactly the kind of long-term, in-place data these 2 aging spacecraft have been quietly providing for over a decade now. When a phenomenon like the magnetic hump appears, behaves in ways that don't perfectly match existing theoretical predictions, and then leaves behind a measurably different environment in its wake, that's not evidence that physics itself is wrong. It's evidence that our specific models of how plasma physics operates in this particular, previously unmeasured region of space still have real refining left to do. Refinement that can only happen Because Voyager 1 is physically there to provide the data needed to do it, there's also a genuinely important practical dimension to this research that goes beyond pure theoretical interest. Understanding exactly how the interstellar magnetic field behaves, how it deflects around the heliosphere, how it responds to disturbances like the magnetic hump, and how consistently or inconsistently it can be predicted from models built before Voyager ever got there, directly affects scientists' understanding of how cosmic rays, high-energy particles streaming in from distant, long-exploded stars elsewhere in the galaxy, actually propagate through this specific region of space before potentially reaching our solar system's protective bubble. The heliopause functions as a genuine shield against a meaningful portion of this radiation, and the structure of the magnetic field just outside that shield plays a direct role in how effectively and how consistently that protection actually functions over long timescales. It's also worth being honest about the very real limitations of this entire body of research, because that honesty is central to understanding why scientists keep describing this data as valuable rather than definitive. Voyager 1 provides a single trajectory through this environment, one specific path through one specific region of interstellar space, at one specific moment in the Sun's roughly 11-year activity cycle. The spacecraft cannot be redirected to sample a different direction, and its twin, Voyager 2, is traveling through an entirely different part of the boundary, meaning researchers are working with two individual data threads, rather than anything resembling a comprehensive three-dimensional map of the entire region surrounding our solar system. Every finding drawn from this data carries that inherent limitation, and researchers studying it have been consistently careful to frame their conclusions as genuine advances in understanding a specific, local patch of interstellar space, rather than universal laws applicable to the entire galaxy. And this research is happening against a genuinely urgent backdrop, because the instrument responsible for gathering all of it is running out of time. Voyager 1's magnetometer remains one of only two scientific instruments still functioning on the spacecraft, following years of NASA engineers being forced to permanently shut down other systems as the spacecraft's power supply, generated by the slow radioactive decay of plutonium inside three aging thermoelectric generators, continues to decline by roughly 4 watts every single year. Engineers currently project that Voyager 1's remaining instruments will lose enough power to function at all sometime in the early 2030s. Whatever the magnetic field out there does next, whatever additional shifts, humps, or structural changes it might undergo in the years ahead, there is a genuinely limited window remaining in which humanity has any instrument at all capable of measuring it directly. So here is where this genuinely leaves things, honestly, grounded entirely in peer-reviewed research, rather than an exaggerated claim about physics itself being overturned. Voyager 1's magnetometer detected something real and unexpected in 2020. A sustained, multi-year disturbance in the strength and structure of the interstellar magnetic field surrounding the spacecraft. Years of careful follow-up analysis, published as recently as May and July of 2026, have shown that this event left behind a measurably different magnetic environment, one whose field direction has continued slowly shifting ever since, and whose full physical explanation remains a genuine, actively pursued area of ongoing research rather than a fully solved mystery. That's not physics being rewritten, that's physics being tested, refined, and better understood, using real, direct measurements from the only spacecraft ever positioned to gather them, decades after anyone expected this 50-year-old machine to still be capable of teaching us anything new at all. If this kind of story is what you come here for, one grounded in exactly what researchers have actually measured and published, rather than exaggeration, hit subscribe and turn on notifications, because there's clearly more still unfolding out there for this aging spacecraft to help us understand. Drop a comment telling me what you think caused the magnetic hump in the first place, and share this with someone who still thinks the physics of interstellar space was fully settled before Voyager 1 ever got there.